Section 9.7, the freezing point depression and boiling point elevation. Adding solutes to water lowers its chemical potential and thus widens its temperature range, which causes the freezing point depression and boiling point elevation. And we can calculate quantitatively the freezing point depression and boiling point elevation. In Chapter 6, for a chemical reaction, we have this formula. K is the equilibrium constant, H is enthalpy, and over here, this is the enthalpy change of the reaction, R is the gas constant, T1 and T2 are two different temperatures. So K1 and K2 are the equilibrium constant at these two temperatures. For a phase transition, such as fusion, we can write out this physical change in the form of a chemical reaction. The reactant is ice, the product is water in a solution with mole fraction X. And then we can use the similar equation here. Okay, Ln(K2) minus Ln(K1) equals negative enthalpy of fusion over R. Now these two are the fusion temperatures. What is K? K is product over reactant. So the product is water with mole fraction X, so that's X on top. And this is pure ice, so the bottom is 1. The mole fraction is just X over 1. So we plug in the mole fraction of K in here. In here, this is just X2, this is X1. And then we use X1 as our reference. X1 is just 1. And then T1 is just the melting point of pure water. So now we have this equation here, Ln(x) minus Ln(1). This is our reference. Our reference is the pure substance. And then we reorganize this equation. We see the melting point of the substance has this simple relation with the melting point of pure substance. Okay, so this is a reciprocal relationship. 1 over the melting point of a substance in a solution is 1 over the melting point of the pure solvent. The pure solvent, in this case pure water, minus R times Ln(x) over the enthalpy of fusion of water, if we're talking about the freezing point of water. Alright, so what you can do is if you add, for example, 1 mole sucrose into 9 moles of water, and then the mole fraction of water is 0.9, so plug in 0.9 here. Plug in the enthalpy of fusion of water here, it's 6 kilojoule per mole. Plug in the melting point of pure water here, it's 273 Kelvin. And then you will get the melting point of this sucrose, aqueous solution of sucrose. Okay. Similarly, for the vaporization of water in a solution, we write out this physical change in the form of a chemical reaction. The reactant is the solution. Water has a mole fraction of X. The product is water vapor of 1 bar. If we are trying to boil the water against 1 bar pressure. And then we still use this equation, and then this time this K, the equilibrium constant, is this. Again, this is 1 bar. Assume it's 1 bar. So 1 bar over P0 is just 1. Okay, the product is 1. The reactant, that's X. So in this case, K is 1 over X. So we plug in 1 over X, and we need a reference. We need a baseline. The baseline is pure water. For pure water, we have this K is equal to 1. And this is the boiling point for pure water. So again, you just need to know the boiling point of pure water, 373 K over here. You need to know the enthalpy of vaporization for water, 40.65 kilojoule per mole. And then all you need to know is the mole fraction of water in a solution. In the previous example, if you put 1 mole sucrose in 9 moles of water, the mole fraction of water is 0.9. Just plug in 0.9 here. You will get the new boiling point of this water in a solution. So as you can see, if x decreases, this part decreases. If this part decreases, this whole thing decreases. This whole thing decreases, that means the boiling point increases. You can do a similar quantitative analysis for the melting point. For the melting point, remember, K equals X. For the boiling point, K equals 1 over X. Why? Because when we are looking at the melting point in the fusion process, this water with mole fraction X appears on the right-hand side. For the vaporization process, this water with mole fraction X appears on the reactant side. That's the difference. So in summary, adding solute to water increases the entropy of water. Therefore, it lowers the chemical potential of water. And this leads to a wider temperature range for this liquid phase. That means you have a lower melting point and a higher boiling point.